Can you hear me yet, Patrick? Not yet. Okay.
Hello?
Yes. Patrick?
Hey,
Hey, got you.
how are you?
Good, thanks. How about you?
I'm doing fine.
Good. You're the first and only one I've seen so far. You don't see any others listed on your screen, do you?
Yeah, no one else is here.
Right. When I get everything open, I can only see usually 2 blocks, and I only see one now, so I figured you must be the only one. Let's see, I guess I'll go on and get started from the current slide. We are recording, by the way. I can't get it to go from current slide, though. There we go. All right, can you see the Chapter 13, Functions of Several Variables?
Yes.
Okay.
Yes.
All right, we're on the same page. I guess first let's start with any issues come up since the last time we met. Nothing?
No, I'm good.
Okay. Let me go. Say again? Were you going to say something else?
No.
Okay.
My dog was whining.
Okay. Here's the only thing, the main things have happened since I guess the last time we met. I think I probably told you about the college is going to a virtual advising center, and they're trying to do everything we did when we were on campus, we're doing on the virtual campus, and that includes advising. So they decided to, well, let's just not give them to every faculty member, but because department chairs don't have enough to do, we'll just have them be our advisors. So whereas I had a limited number of office hours before, as in 2 hours on Monday, Wednesday morning, I still got those. The 2 hours I had on Monday afternoon are now being taken up primarily through advising. Okay, now if I don't have any appointments, then I'm free those times, but you won't know that I don't have any appointments. But you can try to catch me, but if I'm with an advisee, then you won't be able to get me. Then Friday, I had 4 hours of office hours. Those are all now at least possible things for advising. So I went from 4, 8, 10 hours of office hours that were pretty much open to having only 4 hours of office hours that are pretty much open. The others, Monday afternoon and Friday mornings, I'm still will be available if there are no advisees. But I'll usually be checking things after that's over with. And my advising now goes till 7 on Monday, not 6, and it goes till 12 on Fridays. But then I'm required to have faculty meetings on Friday at 12:30. So it's, they're just eating up all of the time as fast as they can. So, and the last time I checked, it looked like, I haven't looked for certain, but it looked like most of my half-hour slots were taken up this evening. I haven't checked for sure, but just on the ones I've seen that popped up on my phone, it looked like most of them were occupied, but I haven't looked at my whole calendar yet. So good luck with catching me during those times, but maybe this first week is going to be pretty heavy, and then it'll probably lighten up some after that. I hope, anyway. All right, and you said you had no issues?
No issues. Fred
Okay.
is here now, though.
Who is?
Fred.
Oh, good. Hi, Fred.
Hi.
All right. So it's 2 of you so far, huh?
Sir.
Okay. And both of you can see the functions of several variables. The interesting thing is I can't see, usually my screen is, my ugly head is up, and then usually I can see the names for up to 2 other people. I see nothing now except what's on the screen, functions of several variables. All right, well, if there are no questions, let's get started. Chapter 13 is functions of several variables. Today, at least by my mark in my memory, we're starting with 13.3. Did y'all have any other things in your marks or memories? Is that where we're beginning?
I believe so.
Say again?
I believe so, yeah.
Okay, good. All right. The objectives in this section, by the way, let me go back. To me, this is the meat of the chapter, the big part of the chapter, partial derivatives. From now on, we'll be doing things with partial derivatives, but the big thing is this is the new thing to learn, and you'll find out it's pretty simple, okay? And what we do with it can get more complicated, but this is the bulk, the main issue in the chapter, partial derivatives. So what we're going to do here is try to find and use partial derivatives of a function of two variables, and then you find and use partial derivatives of a function of three or more variables. Now, up till now, we haven't done too much beyond three because we were trying to visualize everything then. And once you hit the fourth dimension, I can't visualize a thing, okay, or then any beyond that. But then we'll do find higher order partial derivatives of a function of two or more variables, not just a single partial, higher order partials. So that's what this section is going to be tackling. So let's get to tackling. Partial derivative of a function of two variables. Start with it as simple as we can in this section. You can determine the rate of change of a function f with respect to one of its several independent variables. Remember, what a function of, when they say of partial derivatives of a function of two variables, what they mean, and I wish they put it in there, two independent variables. There probably is a third variable there, but that's the dependent variable. That's what the function is equal to. So what we're doing here is two independent variables, okay? And the first sentence said one of several independent variables. This process is called partial differentiation. The result is referred to as a partial derivative of that function f with respect to whichever the chosen independent variable is. So here's the definition, and this is why we had to do limits and all the other things in the first couple sections, so we could have this definition to make sense. If z is equal to f of xy, again, just a reminder, x here is an independent variable. Y here is also an independent variable. There needs to be no dependence on x and y. Nothing. You know, they're completely independent of each other. Z, however, is dependent on both of those. Okay? So, if z is a function of x and y, then the first partial derivative of f with respect to x and y, here's how we designate it. F sub x and f sub y. When you see that, you read it, the partial of f with respect to x, the partial derivative of f with respect to y. Okay? We don't use primes in partial derivatives. Okay? We use subscripts, and they are the variable for which you're taking the partial. Okay? With respect to. Okay? So f sub x as a function, and the partial is a function of x and y, but we're only taking the derivative with respect to x. So that's the limit as delta x approaches 0. Notice that whatever the partial is here, that's what we're taking the limit with respect to. Of f of x plus delta x, comma y, minus f of xy, all divided by delta x. So you see, in effect, the y's are not changing when you're taking a partial with respect to x. Only the x is allowed to change. So it's a function at some value just beyond x, but at the same y, minus a function at x and that same y, divided by the incremental increase, delta x. And similarly, the partial of the function f with respect to y, and again, it will be a function of both x and y, is the limit as the delta y approaches 0. See, whatever you're taking the partial with respect to, that's what you're letting to vary. Okay, and that would be f of x comma y plus delta y minus f of x not changing in this part, comma y. The y part is changing, and then you divide that by the change delta y. Now, that's the partial derivative with respect to y. Now those, provided the limits exist, that's what the partials mean. That definition indicates that z is equal to f of xy. If z is equal to f of xy, then to find the partial of f with respect to x, you consider y as a constant and differentiate only with respect to x. Similarly, to find f sub y, partial of f with respect to y, you consider the x to be a constant and differentiate only with respect to y. Okay? Is that making sense? Probably a little more so when you actually do one. So let's do one. Here is a function of both x and y. 3x minus x squared y squared plus 2x cubed y. Okay? Now earlier they were calling this a polynomial function of two variables. Polynomial meaning that you only have the variables, the only thing you're doing with them are raising them to powers. They can only be raised to whole number powers. Those are positive integral powers. No fractions, no decimals for the exponents, no negatives, only positive numbers for the exponents. As long as all the variables fit our polynomials themselves when standing alone, then that would work. So here's a function. Consider y to be, if you're finding f sub x, we'll consider y to be a constant and differentiate only with respect to x. So you have f sub x, the partial of f with respect to x, and it will be a function of both x and y. Okay? Now, first term. Let's take the derivative of that term with respect to x. What do you get? Anybody? 3. That's it. Minus, now, the next term. X squared, y squared. That has a y in it. Okay, I don't want to completely forget about the y, but do not treat it as a variable. Treat it as a constant. So y is a constant, y squared is a constant. And what's the derivative of a constant times x squared? 2xy squared. Perfect. Okay, third term. It's a plus there. It's going to be a plus. You're only taking a derivative with respect to x, treating y as a constant. What would this be?
6
x what?
y.
Not quite. X squared y. Perfect, perfect, perfect. There, you've done it. You've taken your first partial derivative. There it is. Okay? Let's see how they did it. Okay, they wrote on top. Well, there it is. You can see it. 3 minus 2xy squared plus 6x squared y. Not that bad, was it? Okay. Now that was the A part. Let's go to the B part. Let's find the partial with respect to y. Partial derivative of f with respect to y. In this case, we'll consider the x to be a constant, differentiate only with respect to y. So f, I'm going to write it up here so it won't interfere, f sub y. My pen is not being very agreeable today. It was earlier, but it's not now. F sub y as a function of x and y. Okay, first term. What's the partial of that with respect to y? Notice with respect to y, we treat x as if it was a constant. So 3 say again? It would be 0. Fantastic. Okay, next term. Minus 2x squared. Y. Why not? Okay. If it were right, there it does. Next. Next. Oh, wait. Yeah. I'm sorry. I was looking at our earlier work. Okay. That's still right. Next. plus 2, say again? 2x cubed. Perfect. Okay, there it is. Any questions on that? It's really not that bad. Okay, it's really pretty easy. Let's see how they did it. F sub y, or the partial of f with respect to y, of the variables x and y, is minus 2x squared y plus 2x cubed. Perfect.
Dr. Fowler?
Yes.
Dawson is here. I don't know if you had written him down.
No, nothing popped up on my screen. So Dawson, I've got you. Anybody else come in? I've got 3 of you now. Same 3 as last Wednesday. Okay, Fred, Dawson, and Patrick. No Ryan yet, and no Josh yet.
Josh just came on.
Oh, Josh just came. Good, Josh. Welcome. Okay, still no Ryan. Is that right?
Right.
Okay. I hope whatever Ryan had that had him not feeling well is not this stuff, is it? Have you heard?
I'm not sure.
Okay. All right. And by the way, I failed to mention this. It just seems like I may have said this before, but I don't think I did. On your left-hand margin on page 894, and by the way, for those who just joined us, we're in Chapter 13, Functions of Several Variables, 13.3, Partial Derivatives, the heart of this chapter in my mind. And on page 894, they have a little blurb on Jean Leron d'Alembert. I think is how you sort of say it. A true Frenchman would have been barfing at my pronunciation. But anyway, several things are said here. The introduction of partial derivatives followed Newton's and Leibniz's work in calculus by several years. I don't guess either one of them considered it. So between 1730 and 60, Leonard Euler and Jean Leron d'Alembert separately published several papers on dynamics in which they established much of the theory of partial derivatives. It's, I want to say funny, but it isn't. That it's just so true. So many times physics leads math. I'm sorry to say that, especially Patrick, you're a mathematician, but Newton had a physics problem. He had to invent calculus to solve that problem. So Euler and d'Alembert were trying to work on dynamics, which is usually a physics or engineering problem, and so they had to turn to math, but not just turn to it, create the math to describe it, and that was what partial derivatives came out. Those papers were used functions of 2 and 3, or 2 or more variables to study problems involving equilibrium, fluid motion, vibrating strings, and so on and on and on. Okay, so I wanted to get that done before we left the page. All right, any questions? Seems like to me, oh, this is all the A part. We haven't gotten to the B part yet. So any questions before we move on? Take that to mean no. So let's move on. Here, to find f sub x, or the partial of f with respect to x, and they left off the function, didn't they? That should be an f in there. For f of xy equal log x sine x squared y. Okay, if you're finding the partial with respect to x, we consider the y to be a constant and differentiate only with respect to x. So here's our f sub x of xy. My pen writes sometimes and sometimes it doesn't. Okay, so what would this be? What rule are we going to have to employ here? Actually, more than one. Initially, what? A rule of differentiation. And like I said, there's going to be more than one rule here. What's probably the first one we need to consider? What does it mean for two entities to be written next to each other with only parentheses between them? What mathematical operation? of your big four. Adding, subtracting, multiplying, dividing. Okay, so we'll use the product rule, okay? How does the product rule go? See, everything that we did with differentiation before holds in partial differentiation. It's just we're only going to take it with respect to the x-axis, treating y as if it's a constant. So how does the product rule go?
First to second plus second.
Okay, first here happens to be log x, so I'll write that down. It will write, okay? Okay. All right. Times the derivative of the second. All right, what rule are we going to have to apply here? You have a function within a function, an inner function and an outer function. Chain rule, exactly. So at least for now, let's do the outer one first. What's the derivative of the sine? Not that hard. Cosine of x squared y. You just put the same argument there. My pen will not write. There we go, and it writes 17 times now. Squared y. And then what does the chain rule tell us to do?
Now we add that to the
Okay, not
derivative
add.
of the first times the second.
Okay, not add it to it. Multiply it by it. Okay? All right. And what would be the derivative of the inner term there? With respect to x.
1 over x.
No. Here. Okay. In the product rule, log x, we just did the first. Okay? Now we're doing derivative of the second. Only the second. This part here. And we did derivative of the outer function, cosine x. Now we do the derivative of the inner function. That's that one, the x squared y. What's the partial of that with respect to x? 2xy. 2xy. Okay. I'll put that in parentheses. Okay. Now, why I put it in front rather than at the end, I don't want you thinking that becomes part of the argument. It isn't. So I put it up front so you can tell it's not part of the argument of cosine. Okay? But that's just the first half of the product rule. What's the second half?
Second times
Plus. This is a plus here. And what did you say? I can't hear.
sine squared y.
Okay.
Plus sine x squared y.
Okay. No, okay. Yeah, sine x squared y. I got it now. I couldn't hear what you were saying. That's just by itself. That's the second. And what's the derivative of the first? Someone answered that question earlier. 1 over x. So I'll just put that over x. All right. That's it. Now, we might want to clean it up a little bit and rewrite this as 2xy times log x I can't get my x to write. It'll probably now write 15 times. Well, that's an x. Oh, and change the page and skip down several lines. Oh, what? Yeah. Okay. Well, no, that's not right. We were past that part. Here's where we are. Okay. Times cosine. This is all to get it to write that. I don't know why my pen is not writing. There we go. Cosine x squared y plus, and you can leave this one alone, sine of x squared y over x. It'll go so far and then quit. All right. There we found the partial of f with respect to x of this product function. Okay, now I'm going to pop it up on the screen, and I bet you it'll be right underneath this, but let's see where it goes. You can almost tell it. They put the 2xy at the end. That's okay, just don't think it's part of that argument of the cosine. The parentheses help there. That's why I like to put it in front, and if you needed to, you could put parentheses around it there, okay? Log x times cosine x squared y, and then this, yeah. We got the same thing they do, but just so it's a little more readable, I'll erase ours. But it's the same thing. All right, that's just what we had. We just put this in front. Doesn't matter where you put it. All right, as you might guess, what's the second part? To find the partial of this function f with respect to y, and we consider x a constant and differentiate only with respect to y. So what rule do we employ here? Any guesses?
The product rule again?
Okay, the only trouble is, what's your product? This, the log x, has no dependence on y at all. So that's just a constant, like a. C, whatever you want the constant to be, log x is just treat it as if it's a constant. Now don't change it to a constant, but just treat it as if it's a constant. So basically, all we have is a constant times sine x squared y. So basically, the only rule here we do is what would be, and again, my f we lost here. So f sub y of my parentheses just refuses to write. And okay, there we go, of x and y is equal to what? This is just a constant, write it down. Log x. It's just a constant. No y dependence in it. Now, what's the next part?
Times cosine.
Cosine
X squared y.
Of x squared y. But what are we still?
X squared.
Times what? Times x squared. You're exactly right. Times x squared. And here I especially don't like it out there by itself. So I'm going to bring that in to be x squared log x cosine x squared y. I have to write so slowly for the pen to keep up. Okay. All right, let's see. Yeah, they left the x squared out there. I like to put it in front. Doesn't matter. You can put it in parentheses if that helps. Okay. And again, it won't close that parentheses. Seems like somebody just joined the class, did they? No? Okay. That's supposed to be a parentheses, but it came out a slanted line. Okay. So let's see how they did the partial with respect to y. I think you can almost see it. Log x, cosine x squared y. They leave off the parentheses there, which I don't think is especially a good idea, but it's since they didn't put it before, I guess I don't need it there either. Okay, times x squared. Any questions on that? Is this making sense? All right, that was example 1. Now they're going to tell us some deal on notation. Now, if you remember back for derivatives, first derivatives, we used our prime notation, we used Leibniz notation. We just came up with all sorts of different ways to express an ordinary derivative. Well, guess what? They have a whole bunch of them for partials too. Basically just two. almost the same. The only difference is what we do, the two differences. What we do, instead of a prime, we use subscripts, showing which variable you're taking with respect to. The second thing is, rather than the Leibniz notation, we don't use D's, we use, oh boy, an old guy in my class last term called them, what did he call them? Crooked D's or something like that. Here we'll see them. Here's what it is. I wish I could remember the name he had. For z is equal to f of xy, again we're only doing two independent variables now. Third dependent variable z is dependent on both x and y. The partial derivatives f sub x and f sub y are also denoted with this notation. Let's just call it crooked d by crooked dx of f of xy. There was something he called it was a little easier to say than crooked. I don't remember what it was. No one's heard that before. Whatever. That's the same as f sub x. The partial, this means when you see that squirrely looking d there, okay, that means partial of f with respect to x. Just like sub x means partial of f with respect to x. We can also say partial of z with respect to x, because z is the dependent variable. Or we can say partial of z with respect to x this way. So 4 different ways we can express if z is equal to f of xy, what its partial with respect to x is. And then with respect to y is partial of f with respect to y, or partial of f with respect to y as a subscript, or z sub y, that's partial of z with respect to y, or actually partial of z with respect to y. Okay. Now, the first partials are evaluated. Now, we haven't even gotten into second partials, so don't worry about it yet. The first partials evaluated at a point AB are denoted by f partial of z with respect to x evaluated at AB. This is a point that means A is your x value, B is your y value. It's the ordered pair, xy, only you're evaluating it at AB. So that could also be written as f sub x at AB. A is your x value, B is your y value. Or the partial of z with respect to y evaluated at AB would be partial of f sub y at AB. Make sense? Okay. The partial derivatives, they are skipping example 2. So let's back up and go find and do example 2. I think I'll erase all my ink. Okay. Here's what we'll do example 2. For f of xy, it was writing along so well there and then just quit completely. Okay. For f of xy equal to x, won't write the x. I slow down and everything. There we go. At least the first part. Okay, that's an x. It's an ugly one. E, wrote the first part of the e, but not the second part. X squared y. By the way, usually when this happens, I wonder if there. Let's see if that gets any better. My power doesn't seem like it connecting well. So there's your f of xy. X e to the x squared y. Find f. No, it's not getting any better. Well, the light went off down there too. That's supposed to be an x, y. Okay. We'll also find f sub y. And then we'll evaluate each at the point 1 log 2. Okay? So let's just do f sub x. F sub x. of xy. What rule will we employ to begin with? Anybody? What rule to employ? A lot like last one. Is anyone still there?
Would it be the product rule?
Yes, we start with the product rule. And how does that go?
It's the first term.
Okay, that looks like it's not term, but first factor. Yeah.
Yeah.
X.
First factor.
Yeah.
Multiplied by the derivative of the second.
And what is that?
2xy.
2xy. That part is good. I'm waiting for my pen to write.
Oh.
You're right.
Okay.
You can do it in any order. 2xy. There's more to it.
Times x e to the
Okay, no,
x
no, wait. Okay. The x is out there. It's in front. Times the derivative of the second one. The derivative of the second one, here you use the chain rule. And the chain rule, chain rule part of it, the inner function, that derivative is 2xy. You can do that first if you want to, it's fine. And then times the derivative of the outer function being the exponential function, that's just exactly the same thing. E to the x squared y. Okay, there's the first times the derivative of the second. And those are all multiplied, okay? Now what? It's their arithmetic symbol indicating what arithmetic operation are you doing?
Plus.
Plus, because the product rule is a plus, okay? And then what do we do?
It's
Yes?
the derivative of the first
Yeah.
times the second.
Okay, and what's the derivative of the first? Derivative of x.
It's 1.
1, okay, times the second, which is e. If I could get it to write, it's not writing. I'm trying to write it backwards. Okay, that's supposed to be an e there, okay? Looks like an ampersand. No, not an ampersand, something. The and looking symbol. That is ugly, ugly, ugly. Okay. All right. E to the x squared y. Goodness gracious. Oh, that y should be down there on the same line with the x, but I'm not about to erase it. Okay, there's your partial of f with respect to x. Now, we might want to clean that up a little bit, and I think it's usually a good idea. Let's multiply where we can. This will be a 2x squared y, because these are all factors. 2 times x is x squared y, if the y would write, e to the x squared y, okay, if that would write, but it's not writing well, okay, plus e to the x squared y. Okay. Now you might note both terms, two terms here, both terms have e to the x squared y on them, so why don't we factor that out? You don't have to, but it's, it makes it a little shorter. X squared y, and in the first term what you have left? 2x squared y, second term just the number 1. Okay, so there's your partial of f with respect to x at xy. Now why don't we go on and evaluate it at 1 log 2. Okay, going to evaluate this at, if I could get the A to it right, okay, at 1 log 2. Now 1 is your x coordinate, log 2 is the y coordinate. Okay, so let's do f, if it would write. So far it's not writing. F, it's still not writing. There we go. Sub x at, this time we're going to put it at 1 log 2. Okay, that final answer. E to the, what's 1 squared?
Just
1. And y is log 2. If I could write, there we go, log 2. It won't write. Let's see, it only writes part of the 2. There we go. E log 2 times 2 times 1 squared is still 1. Log 2, that's the y, plus 1. If the 1 would drop, there it goes. Okay. Well, what is E log 2?
It's just 2.
2. Okay. So this answer is 2 times 2, if it would write, but it won't write, 2 log 2 plus 1. Now you could, if you wanted.
The answer is 4 log 2 plus 2.
That is another way you can express it. I was just going to say that, if I can get my screen to clear. Okay. You could write that as 4 log 2 plus 2. Either way is fine. Is that what they give in the book? Yeah, 4 log 2 plus 2. Okay. Now, we're also supposed to take the partial with respect to y and do the same thing to it. I'm fearing I'm not going to have room because I'm writing so big, because I'm writing so slowly to try to get the pen to keep up. Let's try to work it in. F sub y, partial of F with respect to y, first at xy. Okay. And it's always a good idea to evaluate it first the variables, then to plug in. Don't be plugging in ahead of time or everything's going to wind up to 0, because if you plug in numbers for the variables, you won't have any values. I mean, they all have a value. Okay, so what is the partial of f with respect to the y variable at xy? What rule do we apply here? Any ideas? What's the rule? Okay. What you say?
Is it the chain rule?
Just the chain rule, because you see the x is a constant now. You're treating it as a constant. So it's just x times, that constant times, what's the derivative of e to the x squared y with respect to y? That's the chain rule part.
X squared.
Okay, he likes to do the inner first. That's perfectly fine. Derivative of the inner. You just need to do the derivative of the outer. What would that be?
Derivative of e is just e.
Yeah, e to the x squared y. Perfect. All right. Now we can simplify that just a bit. You got x times x cubed is, x times x squared is. Help me some. X cubed. E. If it would write the e, it just doesn't like writing e's. X squared y. Okay. Now we're just going to take that one, f sub y, partial of y, but now evaluate it at 1 log 2. Okay. So let's just take our final answer. 1 cubed is 1. And then you have an e, and 1 squared is 1. And y is log 2. What's e log 2?
Just 2.
Just 2. That's it. And that's all they got. Good for them. All right. Any questions on that? Actually, it's not that bad. Just keep in mind, when you're taking the partial derivative with respect to one variable, keep all the other variables, treat them all like they're constants, and just take the derivatives with respect to that one variable. Okay? And then plug in at the end. But wait, get to the end first, then plug it in. All right. Now we're ready for that next slide. So let's get on through this. This is all stuff from the previous example, and that's what we've already been over that. So here's that next one. The partial derivatives of a function of two variables, z is equal to f of xy, have a useful geometric interpretation. If y is equal to y0, okay, then z is equal to f of x, y0. Because if y is a constant y0, then z is equal to f of x, y0. Okay, now, what does that mean? If this is your surface up here, that pink-looking surface there, that's your z, okay? And what we're doing, here's your x-axis out this way, y-axis that way, z is going up. Your x's and y are your independent variables. They're down here, so your plane, the xy plane, in the global sense, is your domain. Any one of those points, x and y, the x's and y have no bearing on each other. They're just chosen, you might say, randomly apart from each other. Then whatever you choose, x0, y0, if somewhere out here is your x0, say somewhere out here is your x sub 0, and this then would be your y sub 0, then the c sub 0 would be the value you evaluate at this point on the xy plane. This point down here is x0, y0. Okay? And when you evaluate that, that gives you your z0. And that for every point you pick on the xy plane, that's what you get. So you come out here and come back here. You know, that's just how you set up. Okay? All right. Now, so if we're talking about z is equal to f of x, y0, that means you're letting the x be the variable, and y is a constant y0. This is the plane. That blue plane there is the variable, is the value for which y is equal to y0. So it takes that sheet, that curved sheet that was floating along there in space, which is your z, your f function, and it stops it at y to be y0, but then the x's are continuing to move. Well, look at what you got. You've got a function that seems to be doing like this in the xz plane only, at that constant value y is equal to y0. Well, then that function there, you can take a derivative with respect to x, and that would give you this slope here. Okay? That tangent line there is what that first derivative. Only now it's a partial derivative when y is equal to y0 and x can vary, and then we evaluate it there when x equals x0, and that's what you get. Is that helpful in some sense to visualize what's going on? Now the next thing I think they're going to do is pick an x0, which will be right here, and do a plane here, and then you're going to have a curve that does something like this with y. Let's see if they did it. Oh, they don't do it yet. Okay, so your f sub x, that's what we had here. Okay, partial of f with respect to x is the slope in the x direction. By the way, it's easy to get confused here because of the three-dimensional thing. When x is increasing, z appears to be decreasing. So that looks like a negative slope with respect, partial of f with respect to x. Appears to be negative at that point. Okay, so that would be f sub x at x0, and now we're going to evaluate it at x0, y0. Okay, that would be the limit as delta x is approaching 0 of f of x0 plus delta x y0 minus f of x0 y0, all divided by u delta x, and that represents the slope of the curve that you got here when y was equal to y0. That's the curve that plane intersected at that point. Note that both the curve and the tangent line lie in the plane y is equal to y0, because everything that you're doing in this problem is in that plane. Okay. Now they're going to do the second part. They're taking the partial of alpha with respect to y at that same point, x0, y0. So now you come out x0, I had it too far out this way, but x0, that's how far out the x-axis you go. Go along here until you get to y0, which would be right about here. So there's your x0, y0. Then go up here, and that's your z0 there. Okay? Okay? And if you take the partial of that function, f, or z, with respect to y, then you're keeping the x at x0 constant there, and that partial gives you the slope of the tangent line of that curve that's along the x equal x0 plane of that, where it cuts that function. Okay? And that appears to be going down this way. And again, as y is increasing, it appears that the z is decreasing. So that looks like that, the one they happened to show us was a negative slope. Back here it would have been a positive slope, but there it looks like a negative slope. And that doesn't really matter, but I'm just saying, so when x is evaluated at x0, which gave us that plane, and then you take the partial of f with respect to y at that point, this is what you get. And your z0 is simply f of x0, y0. That's that value there. Sort of hard to do. That would be about the value here. Okay. Well, stay up long enough for you to see it. Oh, wait. Yeah. All right. Any questions on that? 3 dimensions are hard to draw on a 2-dimensional plane. And they can sometimes be tricky about whether they're increasing, decreasing, sloping up or down, whatever they're doing. And even finding a point, without a good orientation of the axes, it's real hard to tell where that point is. If they didn't have the colors in here, you just had a point there, you don't know whether it's a negative x, a positive x. It's got pretty much got to be a positive z. So, and a decent idea what why, but not necessarily. You just don't have enough perspective to tell. Informally, the values partial of alpha with respect to x and partial of alpha with respect to y at a point x0, y0, z0 denote the slopes of the surface. It seems like it should be surfaces in the x and the y directions respectively. Okay, so partial of alpha with respect to x would be the slope of the surface. Change of f, or the change of z over the change of x, when y is a constant, and partial of alpha with respect to y would be the change of alpha or z as y is changing, with alpha sub x as a constant. Okay. So here's example 3. I think this is over on the next page, top of page 896. Find the slopes in the x and the y directions of the surface. Alpha of xy is equal to minus x squared over 2 minus y squared plus 25 over 8. At the point 1 half 1 2. Now, cynic that I am, I don't want to believe them until I've verified that when you put a 1 half in for what? What does 1 half stand for? Which variable?
X.
X. Y stands for? A 1 is standing for Y. Yeah, that's the 1. And then we're going to see if this is 2. Okay, when we do, because this is the Z value. So let's plug a 1 half in for X squared. What is 1 half squared?
1/4.
1/4, and then that over 2 would be 1
half.
No, 1 half. No, 1/4 divided by 2. Let's just say you had a fourth of a pie there. I like to think in terms of food. Fourth of a pie, but then you have to split it with your twin brother. Okay, that's 1/8, and that would be a minus 1/8. Okay, plus y is 1, so 1 squared is 1. So minus 1/8 minus 1 would be minus 1 1/8, or minus 9/8. Plus 25/8, what would that be? Minus 9/8 plus 25/8. 16/8, which is 2. Yes, that they are giving us a point that makes sense. Okay, in other words, the problem is well posed. Okay, so find the slope in both the x and the y directions of the surface this way. So what would we be doing? What will give you the slope in the x direction? Ooh, what gives you slopes? The first.
First minus the second.
Okay, no, first derivative is what we're going for. F sub
I thought you
x.
said slope. I'm sorry.
Yeah, slope. That's what to get a slope, you take a derivative. That's what I'm looking for.
Oh, okay.
And try like I might, I cannot get the x. Ah, there it is. Okay. F sub x. And what is your F sub x? Help me somebody. Minus
X.
X. Perfect. Continue. There is no continue because the y squared is a constant and 25/8 is treated, the y squared is treated as a constant and 25/8 is a constant. So that's your F sub x. Okay? Now what they're asking for is what's the value of that at the point 1 half 1 2. So this is F sub x at xy. If I could get the pen to write. Okay. So what is F sub x at the point? I guess I should have put x, y, z, though we haven't been doing that, but no, we didn't. Okay. So what's F sub x at 1 half 1? Pretty easy, actually.
Negative 1/2.
That's it, negative 1 half. Okay, which means if you're coming out the x-axis at that point, parallel to the x-axis, when y is equal to 1, parallel to the x-axis, your z value is going down 1 value for every 2 it comes out the x-axis. That's the slope of negative 1 half at that point. Okay, we also want to find the slope in the y direction, so that will be F sub y at the values x and y. And what would that be?
Negative 2.
2 what? exponent times coefficient, that's your negative 2 times 1. 2 times negative 1 is negative 2. Then you reduce the y by the exponent, yeah, by 1, right? Minus 2y. Agreed or not? Just like you did that for the x, you reduce the exponent by 1. That you reduce that y squared by 1, right? Okay. Now, and the others go to 0 because you treat x as if it's a constant, and 25/8 is a constant. So then you evaluate this, f sub y, at 1/2, 2. And that would be negative 4. So it's really going downhill when you're at that point, 1/2, 1, 2, and you go increasing in the y direction from y is equal to 1, increasing ever so slightly, but x is constantly at 1/2. Your slope is really steep downhill at a negative 4, going down 4 units in z for every 1 unit in y. All right, does that make sense? Okay, let's see, is that all they're asking for here? I think so. So let me erase my scratch here. So we can see how they proceeded. The partial derivative of f with respect to x and y are, and they got it the same thing we did, partial of f with respect to x at xy is minus x. Partial of f with respect to y at xy is minus 2y. All right, good, same as we got. Now we evaluate them at the point 1/2, 1. So f sub y my eyes are stinging. My wife, over the weekend, we sanded down, and our front door, it's an ancient wood door. We got a 1930s house. It's the original front door. Heavy old wood. But it faces due south, so it gets the full sun 24/7, 365 days a year. Whatever sun's out there, it beats out on that door. We can't keep it looking good because the sun just tears up the stuff we put on. So we put on spar urethane, what they use on boats and stuff. So we had to sand it all down this weekend. And that got me a little congested because I breathed too much dust, I'm sure. But then I washed it off with mineral spirits to clean it, get all that dust off of it. And then this morning my wife put polyurethane on it. And that's smelling up the whole house. So now my eyes are just stinging with polyurethane smell. Sorry about that. So if I keep rubbing my eyes, that's it. So in the x direction, the slope is f sub x at 1/2, 1 is negative 1/2. There was no y dependence there, so it's just plug in the x value. And in the y direction, there was no x dependence, so that's f sub y at 1/2, 1 was... Now wait a minute. We messed up, didn't we? We plugged in 2. We should have plugged in 1 there. Remember back here? F sub y at x at 1/2, 1. Either I wrote it wrong, but it seemed like to me we plugged in a 2 there. 1/2, 1. And that should have been a negative 2. You plug in the y for 1. I don't know if I wrote it wrong or just did, but we had a minus 4. That's a minus 2. Still going south, but going south half as fast at negative 2 rather than negative 4. And that's what they got here too. And this is what they've got here. Oh, if we had been paying attention, we'd have looked at this and said this is a z is equal to minus 1/2 x squared plus y minus y squared plus 25/8. By the way, 25/8 is 3 1/8. And look at this. This is a paraboloid, elliptic paraboloid, curving downward because of the minus signs for both of those, and it's elevated 3 1/8 up here. So there's the vertex at 3 1/8, and this is a elliptic paraboloid. These are ellipses around here. The major axis here being something less than 2 there, and a little bit greater than 2. I don't know if they've got that. Yeah, a little bit less than 2 here, a little bit greater than 2 there. Yeah, I guess I'll buy that. Seems like to me that should be twice on the x-axis what it is on the y-axis. It doesn't look like it's quite there. So they don't think you've quite drawn that correctly, but close enough. And the first one we're doing at the value y is equal to 1. There's a slope down of a minus 1/2. And that looks a little bit steeper than minus 1/2 to me. But then over here, when you're doing x equal 1/2, the slope, when you're 1 unit out on y, and that would be here, this value here, then the slope is quite definitely negative, -2. Looks a bit steep. Again, you don't get good perspective when you're in 3 dimensions. It just depends on how you orient those axes. All right, any questions on that? Sorry, I either wrote something down, but I can't tell where I made my error on it. All right. No questions? All right, let's move on to partial derivatives of a function of 3 or more variables. Nope, not yet. We've still got example 4 and 5 to go. I think this is going to be our best place for example 4. Find the slopes of the surface. Where did that come from? Okay. Find the slopes of the surface f of xy. Okay, that's going to be our z, is equal to 1 minus x minus 1 squared minus y minus 1 minus 2 squared. Okay, at the point 1, 2, 1 in the x and the y directions. Okay. Again, before I start, cynic that I am, I want to make sure that this point they gave us is on the graph of that function. So what we're going to do is plug in 1 for your value of x, 2 for your values of y, and do the operations on it and see if you get 1 as an answer. So let's do f of 1, 2, f of 1, 2. I don't know why the pen's not writing. This makes no sense. Okay. Okay, I'm going to leave it alone. Let's see. Since it came up. Well, it didn't come up, did it? Here we go. Okay. Okay. Goodness gracious. Now that polyurethane's giving me a headache. All right, let's plug in a 1. You get 1 minus a 1 minus 1 squared. I think I can do that one. Minus 2 minus 2 squared. What do you get? 1. All right, very good. There we go. So this does give you 1. So this point is correct. Okay. That was just verifying that they did give us a well-posed problem. And I'm always like to check that because it really irritates me to find out after I've done a whole lot of work, oh, we missed that number there. Okay, don't tell me now. Tell me beforehand. Okay, so, and we want the slopes of that surface, that whatever that's represented by, at that point. So what are you going to do? Let's do it first with respect to x. What are you going to do? Anybody? Help me. Yeah, take the partial derivative with respect to, for doing x, with respect to x, first at xy. Okay. Now, what's the partial with respect to x? Derivative of 1. 0. So we're just going to leave that off. Then I'll write down the minus sign because that's what's coming next. Now, the partial with respect to x of x minus 1 squared. What would that be?
2.
Say again?
Be 2 times x minus 1.
Yeah, 2. I can't get it right. My parentheses is really ugly. X minus 1. Okay? And partial of the last term with respect to x.
It's nothing because it's constant.
That's a constant, so it's 0. Perfect. Okay? So, let's just multiply through and see what you get. Minus 2x plus 2. Or 2 minus 2x, however you want to say it. Okay? Now, let's go on and evaluate it. F sub x at 1, 2. And that would be minus 2 times 1 plus 2. If I could get my parentheses to close, there it goes. And what does that give us? 0. Interesting, huh? All right. Let's do it in, with respect to the y direction. That would be your f sub y at, first at xy. Always do it first at the variables xy. What would that be?
Negative 2 times y minus 2.
Perfect. And let's just go on and do that as minus 2y plus 4. Okay. Now let's do the f sub xy, f sub y at xy. And that's equal to what? Oh, sorry. Not at xy, but at, I can't get my eraser to come up. Okay. Not at xy. Whole thing is being really bizarre today. Okay. At the point 1, 2. Okay. So what's your f sub y there?
0.
0 again. Okay. So rather than write the minus 0, I'm just going to put 0. Okay. Okay, 0. Now, I don't know if you have sort of figured out what's going on with this problem. Let's take a look at that. What does that look like it might be to you? z is equal to 1 minus something in x squared minus something in y squared. Just like we had before, that is a elliptic paraboloid. In fact, this one happens to be a circular paraboloid because your coefficients of your x and y are both the same, 1. Okay, now what makes this a little different is you're not, your axis of symmetry is not the origin. It's at the point x equal 1, y is equal to 2. Okay? Well, guess what? That was the xy value of the point in question. So here we have a paraboloid, a circular paraboloid, at the point of its vertex. Well, there, in both the x and y direction, the slopes are 0, because that's the vertex of the entire paraboloid. So it's not at all surprising both of those came up to be 0 once you notice what's going on there. Okay? And I wish they had a picture on the slide set. That's exactly what we've got here. Now, again, I don't care for their graphic here. Well, I can't tell if I care for it or not. I can't, my room, I guess afternoon has come and I'm losing the morning sun, so I can't see my book as well. I turn on the light, that may make it blinding off the bald on the top of my head, but don't be laughing at that. Okay. You know, can y'all see me? Yes or no?
We can see you. Yes.
Yeah, okay. So if I do this, can you see the book?
You have to raise it up a little bit more. Right about there is good.
Okay, you're making me work really hard. Okay, there is the paraboloid down here in the lower left. Can you see that one?
I see it in my book.
Okay, yeah, it's in a little thing. When I look at that, I can't hold it up there any longer, but if you got your books there, that circle at the bottom, I would have thought they meant that's on the XY plane. And if that is indeed what they meant by that, that is way elevated above the point 1, okay? Now, if that's not what it meant, that's just some point way down there somewhere. Why didn't they give the value of it down there? But they didn't. This is up the z-axis just 1 unit, okay? So I can't, yeah, I don't know. Just like I hated it when they didn't show things on the slides in class, I don't like it now either. I can't give you any more insight in what that picture is supposed to be. So, any questions on that? We've done what they asked us to, just I don't like the picture. Okay? So much for that. All right. Horizontal axes in both, slopes in both directions, x and y. Okay, let's move on and do example 5. I think we'll use the same place. Can I erase this, or y'all need it any longer?
I'm good.
Okay.
You're good.
Say again? Good?
So,
Okay.
yeah, you're good.
All right. All right. It won't erase, so there we go. Let's do example 5. The area of a parallelogram with adjacent sides A and B and the included angle theta is given by this formula. You might remember this. I'm trying to remember if we did it in trig or not. I think we did. A is equal to, that's the area A, little a is the first side and little b is the second side, and sine of the angle theta in between those two sides. Well, it just quit writing. Okay. Now, I guess I ought to at least try to draw it the way they did. This is side B. This is side A. This is the angle theta. Okay? And then the parallelogram is something that looks like that somehow. Okay? And we're looking at the area here. It's AB times the sine of theta. Now, how they get that is if you drop a perpendicular here from that point to B, since I drew B, tried to draw it horizontal, and you just imagine that you had a point coming down here. If I had truly drawn a parallelogram, then this little triangle equals that triangle, and this is the hypotenuse A, and this would be B times the, oh, I'm sorry, yeah. Something squirrely here. Yeah, okay. If you did that and chop this off and put it over here, then this total length here is the same as the total length there, okay? Because you took this part off here and moved it over there. So your base is still B, and this would be A times the sine of theta. This height here, I'm going to call it H, which is the opposite side, okay, of that right triangle, okay. Opposite over hypotenuse is sine, so A times the sine of theta is equal to the H. That H is the width of the rectangle, B is the length of the rectangle. So A sine theta is the height, B is the width, so length times width equal area. All right, you probably didn't need to know all that, but here it is. Now, here is the question. Find the rate of change, and when you see rate of change, think derivative. Think derivative. The rate of change of the area, so you're doing D, only this is going to be a partial, I bet. Partial of A with respect to little a. The partial of big A with respect to little a. For A is equal to 10. They don't give any units, so this is equal to 10. B is equal to 20. Obviously, I'm not drawn to scale. And frankly, I don't think the book is either. Okay, so don't worry about that. And theta is equal to pi 6. And I'm definitely not to scale. And I don't think the book is, well, they may be close. Okay? So, what we're looking for, the rate of change of the area with respect to the length of the angled side. Okay? So what we do is take the partial of A with respect to little a here. Now, just to point out to you, theta is not a variable here. It's fixed for the problem, pi 6. B is a variable, but it's fixed at 20. A is a variable, and it's fixed at 10, but we're going to evaluate it at A equal 10, B is equal to 20. But the theta is just fixed, pi 6. Okay? So what is the partial of A, area A, with respect to side A? What would that be? It might look complicated. It turns out to be incredibly easy. Not A. The derivative of A, 1 times 1, 1 times A to the 0th power is 1, right? I just put in my coefficient exponents there. They're all 1s. Derivative of A is 1, right? Yay or nay?
It's just going to be B sine
B sine theta. You got it. Okay? So then you plug in what b is, 20. And does anyone know what sine of pi 6 is?
1/2.
1/2, so this will be 10. If my pen would write, it would be a 10. And it won't write, okay. Maybe it writes, no. Yes, it does write. Okay, and that's exactly what they got. The second part says, find the rate of change of A. That's the partial of capital A with respect to little b. Okay? Rate of change of A with respect. Oh, no, it isn't.
I thought it was theta.
It's theta. I was guessing, not reading. Okay, this time theta is a variable. Okay? With respect to theta. Okay? For the same values. So what would that be? Go back to the original 8, not the one we just did.
So we're going to take the derivative of the sine theta.
That's it.
So it's going to be AB times cosine theta.
Did you say negative?
No, AB times cosine theta.
You're right. Okay, okay. AB times the cosine theta. Okay. My hearing's bad and the line's a little fuzzy sometimes. Okay, so let's plug in our values. This will be A is 10, B is 20, and cosine theta is cosine of pi 6. Anyone remember what that is? Times root 3 over 2. Goodness gracious, that's how a root 3 over 2 comes out. The root isn't too bad, but the rest of it really stinks. But if I erase it, well, the eraser's not going to work either. Everything goes away. This is being so bizarre. The square root of 3 over 2. Okay, oh, and that's a time sign there. Well, 2 will go into 200, or we could have done 10, whatever. That would be 100 times. So here's your answer, 100 root 3, sorry. This one never showed up, but we got it. Okay, 100 root 3. Very good. All right. So basically, what's that saying? Your parallelogram, if you're increasing, say, one of the sides, they said the slant side, incrementally, that changes your area, reasonably. If you're changing the angle incrementally, that changes the angle way stronger. 100 root 3 is something on the neighborhood of 170 something, okay, rather than 10, okay, at the same values. Okay, there I think we're through with example 5. Any questions on it? Okay, we got about 12 minutes left, 11 or 12, is that right?
About 10 minutes.
10 minutes, okay. All right, so okay. Partial derivatives of a function of 3 or more variables. Okay? Guess what? It just goes just like it did before. The concept of a partial derivative can be extended naturally to functions of 3 or more variables. For instance, if w is equal to f of x, y, z, I'm not going to draw a graph of that one. Okay? I'm not going to draw a 3-dimensional very often. I'll never draw a 4-dimensional. I can't handle it. Okay? F of x, y, z. Then there are 3 partial derivatives, each of which is formed by holding the other 2 variables constant. You only take the partial of the one variable. Okay? That is, to find the partial derivative of w with respect to x, consider the y and the z to be constant, differentiate only with respect to x. Similar process is used to find the derivative of w with respect to y, and then with w with respect to z. So here's how they look, and some of the different ways you can express the partial of w with respect to x could also be if w is equal to f of x, y, z. Partial of f with respect to x at x, y, z. These are all independent variables now. So when it says 3 or more, they always intend independent variables. Okay? W is the fourth variable. It's a dependent variable. Okay? So these are all three independent. But when you're taking with respect to x, it's only the limits to delta x goes to 0 of f of x plus delta x, but the yz stay the same, minus f of x, yz. The x has been increased by delta x, but the y and z have not been increased, so you're on those fixed values. Partial of w with respect to y is the partial of f with respect to y at x, y, z, and there you only change your y, and then that change you let go to 0, and it's f of x, y plus delta y, z minus f of x, y, z over delta y. And same with partial with respect to z. You're only taking the partial with respect to z of x, y, z, and that's the limit then as the delta z is going to 0 if you're taking that partial, and your f of x, y, and only the z plus delta z minus f of x, y, z over delta z. In general, if the w is equal to f of x sub 1, y sub 1, x sub 1, x sub 2, x sub 3, all the way up to x sub n, then there are impartial derivatives, and what we should be saying in first partial derivatives denoted by partial of w with respect to x sub k is f, the partial of f at x sub k with respect to x sub k at x1, x2, x3, x4, all the way up to including x sub k and going all the way up to x sub n, where k is any value between 1 and n. Okay, one of those positions there. To find the partial derivative with respect to one of the variables, hold the other variables constant, differentiate only with respect to that given variable. All right, here's example 6. Is that the next one in the book? I think so, over on page 898. To find the partial derivative of f of x, y, z is equal to xy plus yz squared plus xz with respect to z. Why do they do the work for you? I don't know. Just pretend this isn't here. Okay? We'll do it. With respect to z. So it's f sub z of x, y, and z. Okay? And what would you get that to be? Anybody? F sub z of that function f. It's the derivative of xy with respect to z. Say again? 0. Perfect. Okay, the second term. That's partial with respect to z? 2yz. 2yz. Perfect. And the last term?
Plus x.
Plus x. Perfect. You got it. There's the partial derivative of f, of that function f with respect to z. Okay? And I will pull up the veil so you can see what's underneath. Ooh, if I do that, let me do this. Okay. All right, and there it is, 2yz plus x. Okay? We'll do the b part and just pretend, whoops, pretend we can't see. I need my pen. Pretend we can't see all that. Okay, so here we're doing with respect to z again, f sub z. And I'm going to leave off the other part because we got a lot to write. So, what are we going to use? I ought to erase all this too. What do we use? Did someone say product rule?
No.
Yes. Okay, good. So how does that go?
First, D, second,
First,
second.
which would be just Z times product rule. First times derivative of the second. And the second is that sine function there. What's the derivative of the sine? Cosine of, at that value, xy squared plus 2z. But then we got to use the what? Chain rule. Okay? And what's the chain rule on the argument there? Xy squared plus 2z. What's the derivative of that with respect to z?
The x, y squared is 0.
Yep, that goes to 0.
And then the other one is just
2. That's it. I'm going to put that 2 out front. No reason not to, and it just sort of fits better there. Okay, so there's the first times the root of the second. What do we got to do next? Plus, yeah, add to it,
second,
which is sine of xy squared plus 2z times the derivative of the first, which is
0.
no, derivative of z is not 0. 1, exactly. So I just didn't even write the 1 down. So there's that partial. Okay? Now, I'll erase my erasure here, or my line out here. Okay? And we'll even erase that part too, just make it look a little better. And we did the first part. We did z times the partial of the sine with respect to z. We already calculated it, plus sine of that times the partial of z, which comes out being z times cosine xy squared plus 2z times chain rule 2. I put that out front, and then plus sine of x squared y plus 2z with the chain rule derivative with respect to z. No, of z is 1. Okay. So that's exactly what we got. They put the 2 over here, we put it out front. Other than that, it looks the same. Oh, there they did. Now they moved it out front. 2z cosine x y squared plus 2z plus sine of xy squared plus 2z times 1. Got it. Any questions on that? Oh, there's a C one. Good. And let's just pretend that, oh, this is a 4 term. Okay? So we don't, yeah, we just don't want the last part. Okay? So we want to take the, what's that? Out of time? Okay. We'll pick up with C next time. Actually, we got just a tad further than we did last time I taught from here. I'm surprised because this is so slow teaching it this way. In class, I thought it would go faster. Okay. Homework exercises here. Oh, we almost finished 13.3. You can do any of the odds 3 through 9. They're all at Calc Chat. Any of the odds 11 through 39. Plenty of those, aren't there? They're all at Calc Chat. 13's at Calc View. 41 or 43, they're both at Calc Chat. 41's at Calc View. 45 to 51, they're all at Calc Chat. 45's at Calc View. 51 or 55, they're both at Calc Chat. 53's at Calc View. 57 to 61, they're all at Calc Chat. 57's at Calc View. 63 to 67, they're all at Calc Chat. 69-275. They're all at Calc Chat, I think. I mean, they should be. What I'm thinking is, let's stop there, because we haven't done second partial yet. So that should be enough to get you going until Wednesday. You think you'll make it? Good deal. Any questions? Then we'll see you on Wednesday. Be safe and take care. And I think I've lost everybody. You didn't want to hear those assignments, did you? Okay. So what I think I'll do is